Ulfar had previously been at Microsoft and had been a professor at the University of Reykjavik, had done a couple of startups. He's a very broadly knowledgeable security person, as you'll see, but also one that is interested in applying the newest things to make a difference in an extremely important domain, because we all know there are significant security concerns on the internet broadly. He'll be talking about the intersection of how security and cloud computing fit together, which is exactly the bridge we want as we move from cloud computing and the main agenda into security. Ulfar, thank you.
Yeah, thanks. So maybe I'll start by talking about security research at Google, since I actually joined into Google Research. And so people have asked me multiple times already since yesterday, sort of what's the difference between research and the rest of Google. And to be fair, really there isn't much difference. So Google has a very integrated research and development sort of environment. And so both in all of the product groups, the infrastructure and other groups, there is actually what one would think of as research. There's also a security group, and Eric Gross leads that and will give a talk this afternoon. And there's lots of advanced work there on security, privacy, cryptography, and so on. So if there, maybe within Google Research, the difference would be slightly longer term focus, more external collaborations, although there's a lot of those already from our researchers, and there's over 100 or just about 100 publications that are on the research website in security, and a lot of those are in collaborations with external parties. So the eventual goal of trying to look longer term is that security is not exactly where we'd like it to be, and so it's worthwhile to try to actually attempt taking a slightly larger step forward. And so on that, I'm going to talk about security and cloud computing, and I feel kind of embarrassed because I just joined Google recently, and so unlike a lot of the people here, I haven't, and the people that will be giving talks this afternoon, I have not been working on this exact topic, security for cloud computing, for a long time. Unlike Andrew Fikes, I haven't actually built real massive systems that serve millions and millions of users. But I'll try to give some perspective, at least, and maybe starting with sort of how is this different from what comes before? And of course, there has been large infrastructure and plans for large infrastructure multiple times throughout the years, starting with maybe Multics, but even earlier time-sharing systems. And there have also been online communities, starting with systems like the Plato teaching network in Illinois in the 70s, and all the way through bulletin boards and multi-user dungeons and CompuServe. This is an ad for socializing over the internet, or actually not the internet, but over the CompuServe network from 1983. Feels quite appropriate for what people like to do today. Or is cloud computing really maybe more similar to scientific computation? Large data centers, lots of machines, and lots of important data that's being processed that needs integrity guarantees, et cetera. And so in trying to resolve this in my own head and trying to figure out, so what is cloud computing security, looked a little bit at the NIST definition of cloud computing, and also was at an ISAT workshop a couple of weeks ago where this was sort of a recurring motivation. And so the NIST definition of what is cloud computing really feels quite similar to what one would think of as scientific computation. So it's these very scalable network services, these massive capabilities, and then you have good access to them, and the access is metered or controlled in some way. And there's a categorization into software platforms and infrastructure, but overall it's very much a infrastructure-like definition, and a lot of the thinking has sort of been in that vein. Although security is perceived as a top obstacle. And so maybe coming from the outside, I'm a little bit more naive than people that have been working for a long time on the infrastructure. But to me, what seemed to be sort of maybe more interesting were the existing very successful cloud services, what one can really think of as being cloud, things like Gmail, things like YouTube, Blogger, even the image sharing and Picasa and so on. And so I observed that there's various commonalities that seem to be sort of more to the line of thinking where I would think that cloud would be, and how that touches on security. And the first one is the really strong focus on users and data. So cloud being really about focusing on the user, and moving data that previously sat on various devices or in homes and so on into ubiquitously accessible cloud services, where they can also be more easily shared, even when you have very large or complex data items, where they can be more easily maintained up to date at the very latest fresh copy. So instead of having multiple email boxes in various places that you have to synchronize and so on, there's one of them. And where you also have more reliability, because unlike any one of these devices where you had, one might have a copy of the data and that might somehow get lost, you actually have multiple copies and redundancy in the cloud. And of course, this centralization of user data cannot be done without giving the users control of that data. And Google has been very good at doing that and dealing with the issues in privacy, authentication, and public policy. And we'll hear more about that this afternoon. This logo is from the Data Liberation Front. Of if users give data into these cloud services, they should be able to take them out and permanently take them out. Now, of course, there is the massive scale, which we also heard about this morning. And so to actually utilize all the world's information, well, all the world's information is getting larger all the time now. A lot of it is video. So as every single device out there seems to have a video camera in it, and videos are very large. So the infrastructure needs to get larger and larger and larger. So Jonathan Smith, in this ISAT study from UPenn, had a very nice sort of term for what one really would like. One has a short query and infinite data sort of in the back end. So you have a very easy way to express this simple query you want to make, and you have this infinite data set that's infinitely available and fresh and so on. And you want fast answers that are correct and up to date, even when machines fail, and machines will eventually fail, without doubt. And to deal with that, of course, you need redundancy, but you also need redundancy just for availability and performance as well. And since all kinds of partitions and so on can happen, you need even geo-distribution of redundancy. And this redundancy is not just on the server side, it also has to be on the client, which really comes into the client needs to be mostly stateless, which also helps utilizing a new client to access your data. So clients can fail, so they have to be stateless. Now, a third property that seems to be common amongst all these popular cloud services is there's really a new definition of software, where software is the first time, well, as you just opened that web page, you got a new copy of the software. So maybe you had some previous version of the software cached already. So large properties like Gmail have a tremendous amount of JavaScript and other code that actually is used to implement them. But through caching and various other means, you're always running the most up-to-date version of that software. And this, of course, simplifies greatly management. You don't have any applications to install or remove or maintain up-to-date. So even on the desktop, as we'll see in a little bit, we're actually getting to this point where you're always having the most up-to-date version, which of course helps with security vulnerabilities, making sure that any fixes for those are actually in. It also helps for all kinds of randomized experiments and instrumentation. It helps with fal-stop error handling, because the clients are actually stateless, or even in the server, you have redundancy and you also have statelessness. You actually have all of a sudden this very draconian measure of if you think something is wrong, you actually can do that. You can roll out new versions incrementally, etc. So as a final sort of going back to the user, there's really a new user model of what is software, what is an application. And so as a user picks one of the hundreds of thousands or even millions of applications to use at this particular time on their device, they're really interacting with a single user device that may be running multiple applications. But each of those applications on that local device is relatively isolated. So they can communicate through the cloud, but within the local device, up until this point, in the different implementations of this on phones, in web browsers, and so on, local communication is actually not that easy. So this is actually very different from the time-shared multi-user systems of the past. So this is really a relatively fundamental change, especially when coupled with the malleability, this very dynamic nature of software, and the scale of the backend cloud services. So that's sort of my short summary of what is cloud computing. So it's a particular point of view, but I think especially this notion of the different application model, that's really a big change that's happening, and I'll get back to that later. Now, what are the challenges here? And so in all of the existing large-scale infrastructures, be they bulletin boards or MUDs or even games, you always have security problems. And commonly when you have users, you have the same security problems again and again. So people would hack into bulletin boards for various purposes. People would cheat at games, et cetera. So when you have users, when you have something to gain, you will have people trying to actually get those gains. And so that's one commonality. Now, actually, in this new world, the biggest new thing, because there is this emphasis on user data, is really privacy. And so there really have to be means for pervasive privacy protection. And there's actually a lot of research to be done, a lot of work to be done on that topic. And Betsy Masiello will tell a little bit about what Google has done on that in the afternoon. Also, Dirk Balfans will talk about authentication, which is another big topic. So to protect the user's data, you actually have to control who is accessing it. Some data might be completely public. Other data might be for your eyes only, other for families or people you have chosen to share with. And what's interesting is that this relationship has to continue for the long haul. So cloud services are something where you put the data in, and you might actually keep it there for a long time. And then the final thing, which actually is sort of where I have done most of my research, is really the problem that software has bugs. And so one actually has to deal with the fact that software is not correct, software has bugs. Those bugs should not allow arbitrary things to happen. Now, just looking a little bit deeper into this, so Google has as one of, if you look at the Google web pages and sort of about the company, one of the things that's very prominently displayed there is the privacy principles. And this is very nice, sort of in the spirit of what Alfred was talking about, the setting some clear objectives and then working towards them. And the first one is simply that any information that's brought in is actually utilized to create value for the users. So collection of information is not just there because it's actually there to bring valuable services to the users. And all of the processing and utilization of that information is in accordance with the highest laws and privacy standards in the sort of state-of-the-art practices. The user is aware of what data has been collected, so making all of this information transparent, and they have choices. They can take the data out, they can delete it, they can move to another service provider in particular, they can choose to have certain data not be collected, et cetera. And then finally, because the data is there and it's in massive data centers and so on, a lot of effort has to be put in place to protect it. So to the question that Emmett asked earlier about, is data actually lost? So absolute emphasis has to be taken to actually protect the user's data. So on the next sort of these 3 points, privacy, authentication, and software security, I was struck when actually going through making these slides that some of the longest relationships that I've actually had in my life have been with cloud service providers, because I got, yeah, so so I was realizing that sort of about 15 years ago, I opened these email accounts, and they've been accumulating information since then. And so really all that's protecting that information from being deleted or from having, some bad access is somebody getting a password. So that actually we have to work on improving that, and we have to work on making sure that we really have strong guarantees both about losing the data, but also about who is accessing it and so on, the integrity and availability. And I might have an accident. I might not remember one of these passwords. I sometimes have difficulty remembering them when I don't log into some of the early cloud services that I became a member of. So I have to struggle. So maybe one day I'll forget that password. So it has to be a mean for accounts recovery, but that cannot then be a means for getting other people's data. So I thought that was sort of an interesting observation. But so to the sort of point where I actually know what I'm talking about and where I've actually done research, and which will be sort of most of the rest of the talk, is software security. And software security really stems from the fact that computers don't obey people. Computers obey software. And you don't really know what the software is doing. You don't know how it's written. You don't know what behavior may be induced in the software for any given set of inputs. Certainly, even the best and most benign software will have some bugs. And care has to be taken to actually constrain what can happen despite those bugs. And so even the most basic questions like what software are we running? Is this a particularly known bad piece of software? What's going on right now, is that really what should be happening? If something bad happens, can I get my data back? So those are all traditionally extremely hard questions to answer. And so one of the things that Google has been working on is actually to try to make those questions easier to answer in various means. And so I'm going to focus a lot of the rest of the talk on that. So really improved security, in particular for the cloud client. And I'll sort of explain why I focus on the cloud client. So the data center, we control. We have very good people. We have lots of very good people. You'll meet many of them this afternoon. And we sort of have a handle on what's going on there. State of affairs is relatively good, sort of comparatively. So this is actually some slides that I took from Brad Chen, who gave them sometime last year. And so the client is messy, and there's a lot of sort of bad elements. The rule of law is not all that it should be, maybe. So you don't really know whether your machine is part of a botnet controlled by somebody trying to send spam or for other nefarious purposes. And you don't really know where information is going. There's no real strong guarantees about privacy, etc. So it's worth trying to really change that. And so going back to this notion of actually the way applications and software works is really changing quite rapidly. You have these locally isolated applications that are connected through the cloud. And so instead of in time sharing where you had multiple users and so on the Android phones, user accounts, it runs Linux, so it's sort of on that legacy of multi-user operating system, but it uses the user accounts for different applications. So it's really application accounts. It's not user accounts. And this is partly because applications really should have different rights. The right to access email services and potentially update your valuable cloud information should not be given to a particular game, etc. So a lot of the work that Google has done that's very impressive, at least to me when I was outside Google, is on the Chrome web browser. And so it's fast, it's simple, and it's secure. And it really is quite an improvement. Sort of the aim was for a fundamentally more secure web browser, and I think to a large extent that has been a success, and it's also influenced the other main browser vendors. So it's an open source project, so everything is pretty open. Google Chrome is really the packaged instance from Google. And the basic security story of the architecture of Chrome is really to move the expectation of the user closer to reality. And actually move reality closer to the expectation of the user by having sort of a more read-only experience of the internet. So when you visit a web page, arbitrary things should not basically happen. So you have this green border here around all of the activity related to going to this web page, and so all of the effects should be contained within that green border sandbox. And there's various other technologies that are implemented in Chrome as well, phishing and malware blacklists and so on, and they've been really leading in security features. One of the things that they've been leading in is actually making software updating faster. And so it's interesting to note that according to some public statistics that I saw, 10% of web browsers, users of web browsers right now are running a version of a browser that really started in 2001. So they might be running an up-to-date version of that, or the latest released version, but really they're running a web browser from 2001. So Chrome has a built-in auto-update functionality which downloads in the background latest version of the browser, and then next time you start a new browser instance, it will actually use the most up-to-date version. So this is relatively seamless from the point of view of the user, and it seems to really work. So here are some various browsers, and on Google Chrome, we're seeing that more than 90% of the users are running the latest version of the program within a week. So which is quite an improvement from running something that was really built in 2001, which is 10% of users right now. So so there was a recent announcement that they're actually moving to a 6-week update cycle. So this will happen every 6 weeks, basically, that there's a new version of the browser, and then within a week you should see a curve like this, 90% of users. Now, of course, this will help with getting fixes to bugs out there. But that's not all you have to do. You also have to deal with the bugs that you haven't fixed. And there's a wide range of mitigations and technologies you can apply there. You can randomize the address layout. You can use various stack cookies and so on. So this sort of general term is mitigation here. And there's various things that are actually applied there. And a new one that I learned of only recently is, for instance, not allowing instructions that perform direct system calls from the regions of code where just-in-time compilers, like the JavaScript just-in-time compilers, puts their output machine code. But this raises the bar, but attacks will really still be possible. So even more sort of strong guarantees are warranted. And that's actually where one of the really impressive projects, I think, that Google has spearheaded is making some ideas that actually started in the late 60s, but were really revisited and made concrete in the mid-90s on software fault isolation to make those ideas really reality. And there's this native client project, which is, again, an open source project, which aims to make machine code, the code that really runs on your computer, as safe as JavaScript, or as running a new program should be as safe as visiting a web page. And so there's an open source implementation for now 3 architectures. And what's important and interesting is this really allows for arbitrary low-level, even optimized code that uses SIMD instructions and so on to get really good performance. So actually making more efficient use of the world's computing infrastructure. In particular, it allows, so the guarantees that it gives it come from being able to see exactly what code is. So those were one of those early questions that I said are surprisingly hard to answer. It's like, what code am I running? And native client actually allows seeing exactly what machine instructions, what will the hardware be actually utilizing. And by doing that, you can actually circumscribe. Like if there is no integer division instruction, you know that no such operation will actually happen. Or more to the point, if there's no debugging system call, you know that no debugging system call will actually be executed at runtime. And this comes at some performance cost, but that performance cost is actually much less than the gains you gain from going to low-level code. So if you tried to implement this in JavaScript or Java, you would actually have more performance overhead. And so the aim here is for high assurance. So there's both academic papers, Oakland, sort of the IEEE Security and Privacy, and Usenix Security have papers on this in the last couple of years. And there's also been a public bug competition, et cetera. So I won't really go into the details, but suffice it to say that there are slight changes into what actually is the machine code that executes on the system. This is where the overhead comes from to some extent. And in this case, it's really just making sure that when you're jumping around in bytes that actually determine behavior, that you have a certain alignment property, that you know you're actually going to a 32-byte aligned block. And those are the blocks that then can be stitched together in arbitrary sequence. So this is a relatively weak form of something called control flow integrity. But looking individually at each block, you can actually figure out what are the possible machine code instructions that might execute. So why do this? Well, web applications. We want lots and lots of apps. And the users want lots and lots of apps. And there, at I/O, Google I/O, there was an announcement that there's actually going to be a Chrome web store where you will be able to get lots and lots of apps. And those apps might actually come as very rich native client applications. And here are some examples of applications that exist already. I'm not particularly thrilled about this Lego character. So it's a Star Wars Lego character. I wish there had been a sort of more pretty one that I could find in a screenshot. But here are 3 example applications that actually run at relatively native performance with 3D graphics in your web browser completely safely, as if this was an image on a web page, or at least that's the goal. The goal is a high assurance guarantee of that. And the anatomy of the internals of such an application is basically as follows. You have some application, in this case a calculator. Actually, behind the scenes, it's composed of JavaScript and a red module, which is contained by the native client sandbox. And the red module is just purely native machine code running directly on the hardware. Now, the native client sandbox and this module are actually sitting within a new plugin interface that has been developed by Google called Pepper. So, and there's the NaCl, and Pepper sort of makes sense if you think about it in certain ways. Now, so the JavaScript component then would dictate high-level user interactions, mouse input, and so on. The Pepper plugin interface, which is a new variant of the NP API, Netscape plugin interface, actually is then hosting the rest of the program, which might in fact be most of the work happens there. All of that work happens within the sandbox, and the sandbox is really driving the execution of these bundles of aligned 32-byte sequences of machine code. So with this, you can actually imagine a platform, a whole platform, where you have lots and lots of rich applications going all the way down to the lowest layers, sort of extending this notion of trying to have low-level security. That is a very rich platform and offers good performance. Now, one of the things that you would want to know there is, again, what code am I running? And once you get into the sort of operating system realm of things, you actually boot computers, and you would like to know, well, what have I just booted? And so in the Chrome OS, which is sort of the extension of the Chrome effort into hardware, that is actually going to be an implementation that sort of for that particular type of open consumer device is the first one that will allow verified boot, where the very early firmware that's on the device actually will verify the next state of the operating system, and then that actually will verify the final stages and the applications, et cetera. And importantly, this will allow people to have guarantees that even if they lose their device, or there's somebody installs the wrong operating system or something, their data won't fall into the wrong hands. So the data will be accessible only when they're running the real operating system without any rootkits, et cetera. So I'm going to just speed up a little bit. I'm not going to talk about the details of this, but I'm going to go back up to the user. So all of this low-level security is not going to be very important unless you actually have secure means of communicating with the user. And that really means giving the user abstractions and ways to think about things which are actually come somewhat naturally, but also fit with what actually happens underneath the hood. You have to sort of remove the impedance mismatch between various security dialogues of asking questions. Do you want to allow this strange thing you don't really know what to do this strange thing that you also don't know quite what to do? Is the wrong way of doing things. So you have to have abstractions and mechanisms which are closely aligned with the user's models, mental models, and with how things actually work. And so one of the things that we have started in Google Research since I joined is actually an effort to look into those types of secure user interfaces that provide stronger security guarantees and also high usability, using capabilities as sort of the way to think about things. And capabilities have some promising sort of intuitiveness properties. They're also a principled abstraction that can be distributed, and all of these cloud computing applications are distributed, and they can go all the way to the lowest levels. So with that, I'm just going to finish with a couple of slides on what are the cloud opportunities. I'm afraid I went a little bit over time maybe, so there's not a lot of time for questions, but we'll see. So the real opportunity here that I think is changing with cloud computing is this new application model. This is very different software from multi-user shared computer software, where you had a single server with multiple users connected in, trying to protect against each other. Typically, in the days of the design of that software, each of those users was also a programmer. If the machine in the center actually went down, if you actually had to terminate some processing there, that was a very big deal for potentially all of the users. In particular, if there was a shared service like the file system or something you thought might actually be having trouble, terminating that would actually cause everybody to suffer. So we know about planned outages and so on. So this is the new model of software is also different from the model of software of client-server computing in the 80s, where you had relatively thick clients, and you had, again, these shared servers. And if a thick client servicing some purpose actually went away, people were not all that happy. It might be difficult to reconnect back to the server, establish the session, et cetera. You might lose even state on the server. So the new application model is really one of logical applications that really exists sort of as an emergent thing in the cloud. You have millions of applications, you have billions of users. Each user has lots of devices and is running a number of applications at any given time on those devices, but none of that really matters. The applications are logical. So, and you have location and device transparency. So thinking of this as the end-to-end distributed systems actually seems to be the right way to make progress, at least from the security point of view, as far as I can tell. And so important there is the statelessness of the devices and the malleability of the software. So one can really determine what software is running on any given one of these machines, both in the backend, in the server. Each of the servers that's in the replicated instances of this software might actually be slightly different, might be specialized to a purpose, might have some randomized instrumentation or experimentation applied to it. Again, fal-stop enforcement is actually an option across all of these machines that provide the logical application abstractions. So, and just as a final point, one thing one could possibly do is actually to leverage what my colleagues here at Google have written a paper, Peter Norvig and yeah, so Peter Norvig is one of the authors on the unreasonable effectiveness of data. So when you simply have a preponderance of evidence that something is in a certain way, you can actually take that as the ground truth and say, conservatively, that will be good enough to allow all good behavior. And the example that might be useful to think about there is the solitaire game on Windows, which was there already in Windows 1.0 and has moved forward. Now, the solitaire game throughout all these years and even today can do absolutely anything you can do. And it can do any networking. It can debug other applications. It can definitely grovel through your file system. And that's kind of wrong. And it certainly doesn't fit with this new model of thinking about applications and assigning rights to applications. But how do we actually figure out what the rights are? Well, throughout those 25 years of the lifetime of the solitaire game, it actually hasn't been debugging other applications. It hasn't been groveling through file systems and sending data over the network. So that type of preponderance of evidence can certainly be applied to determine those types of models. But of course, there's lots of other things, like which parts of the program are slow and buggy. So it's not just for security, which parts are dead code. So actually eliminating dead code is a very important security goal. And the nice thing here is that we can sample both the good executions and the bad executions and compare and contrast. So anyway, with that, I'll take questions. Yeah.
Yeah. How do your comments relate to zero-day attack?
So that's a fine question. A lot of security is reactive and pattern-based and so on. Everything that I sort of talked about in the middle there, in particular native client and Chrome and so on, tries to be proactive. And so it tries to actually build defenses that innately give strong guarantees. Now, you may still have zero-day attacks, but you will have switched where they might occur. If you really have strong guarantees, then you will know that they're not zero-day attacks that are violating those particular guarantees. So that's one way of answering your question, is try to actually have strong guarantees in some areas. And at the level of the machine code, simply knowing that execution proceeds via a sequence of 32-byte bundles is a very strong guarantee, but it's a very weak guarantee at the same time. But it turns out that just that simple guarantee allows you to make other guarantees as a consequence. And so starting from sort of bottom up is one approach. And of course, there will be zero-day attacks because there will be security vulnerabilities at various levels of the system. And so I'm from the Nordic countries, so there's the joke of the Norwegian virus, which is an ASCII text message, which asks you politely to forward to all of your friends and then delete all of your data. And now, yeah, this is within the Scandinavian countries. You make fun like that. But so you will have. So the Norwegians are honest. They do, if you ask them politely, they might do it. So but it sort of goes to show that you will have problems at various levels of the systems. That's not a phishing attack. But you actually have to take a multi-tiered approach. So, any other questions? Yes.
Multics used to have 11-layer models. Does that model still apply here, or revisiting that again?
A sort of ring-based protection model. Yes, in fact, in various. Sorry. So the question was, what about Multic's ring-layered protection model? So they had 7 rings of protection, maybe based on Dante, or I'm not quite sure. So where at the core there was something very small and very secure that you had strong guarantees from, and then as you moved further out, you had fewer guarantees and sort of more permissiveness. And I actually think that sort of pervasively, yes, we're going to see more and more of that. And so back to the sort of notion of this verified boot. As you go up the stack towards applications, you're actually allowing more and more things to happen. And now, the Multic's ring model was not really a huge success in hardware and so on. So there have been implementations like the 386, but typically only use 1 or 2 rings. But actually, I think we're seeing more and more layering of software. And this goes back to the talk previously about layered storage services. So at each level of those layers, you need guarantees because you're allowing more permissive behavior above you. So, yeah.
You talked about the Google type of cloud. There's also another type like Amazon E2, where virtual machine has to be used as instantaneous for cloud. Could you also comment on that?
So I think eventually, if you look at how a lot of those things are used, you actually have applications that look very much like what I was describing running on top of those back-end services. So, but I guess there's a number of things you actually need to do when you're running back-end services in general. And there's some new things that are exposed when you try to resell, like Amazon does, those back-end services. And that's sort of in the NIST definition of things. But there's not a whole lot of new security challenges there that I could identify. So I guess that sort of has to suffice. I think, yeah, okay. Yes. Right. Yeah. So maybe back to the sort of, what's the real change here? Having infrastructure that you can run on is a change, but it's a new form of this centralized multi-user computer that we actually have been using since the 70s, or the Multic security model. You have a centralized service, you have lots of parties using that server with maybe, different interests, and you have to do this securely. So there's been a lot of work in that field. I think this new application model and the focus on the user actually is a bigger change because it fundamentally redefines what is software, how does it work, in a way that hasn't happened before. So I think we actually should go and have lunch, unless there's more questions.
Thanks very much.
Yeah.